Hi everybody, this video is for report number 7 for CS206 final project. If you do remember, our main objective of our project is to do an altitude control using genetic algorithm. And in the last few videos that I've done till now, I've showed you my quadcopter system and how the controller is essentially being used to control the altitude of the quadcopter. So in this particular video, I'm not going to show you a lot of simulation because it just takes a lot of time. But what I've been doing so far in the last video is I was able to generate a population, and then from that population, I was able to randomly create a proportional and integral. So KP and KI values for our controller. And from that, these values were then implemented over here. So this is my controller. So when I designate a KP value in my workspace, it comes over here and then it is implemented to our system. And then this is the whole system for the quadcopter, which then results in the working of our quadcopter system. In this video, what I've done so far is I've made some modifications to my script, so to my genetic algorithm. So what I've done so far is that let me just open up the file, my code launch. So what I've done so far right now is that initially I provided very good values for my controller. So I knew what the proportional and integral value are likely to be, and I was using a Gaussian random generation number. So I provided a mu which was close to what my value for proportional controller was, and for a mu for the integral. And then I provided some standard deviation, so the random generator would pick values close to my mu. In this case, what I've done is, since in the previous video you could see that since my value was very good, or my first initial guess was very good, then that's why my initial results were so good that my fitness values were very high. So but in reality, what would have happened, or what should happen, is that regardless of how good or your values are, you should improve your genetic algorithm should be able to improve towards or to find the most optimum solution. So for this case, what I've done is essentially I've created a function where the user provides initial values for KP and a sigma. So it's basically a histogram. So you're creating a histogram, not a histogram, but you're creating a bell curve with a given mean and a given standard deviation. And then your pop generator essentially uses that to create a population for KP and KI. So these values could be correct, could not be correct, and the whole purpose of this is that even though if your values are not correct, how do you come up with a solution that is good enough for you? And actually, I would like to actually just show you how this works. So essentially, let's start with this. So copy this and go to troubleshoot. So there is a troubleshoot over here. Okay, so let's just do one thing. Let's just provide these values to control R over here, and so let's generate values using mu kp, mu underscore kp, sigma underscore kp. So I provided these two values for kp, and now hopefully it works. X of n. Okay, so I have to do this as well. So mu underscore kp, sigma underscore kp. So this should be good enough now. So what happens now is that the user provides a mu for kp is equal to 20 and a standard deviation, which in this case is 2. So now what would happen is that my system will be able to get any value between, let's say, 12 to 25. So when I use a random generator, my these will be my initial values. So my values could be anywhere from this range. Of course, if we do know about normal or Gaussian distribution, we will know that most of our values will be in the range between 20 to 18 or 22. So this is a standard situation which is known to us. Now what we want to do is we want to move this mu or mu kp to a value which should be closer to the one that is expected. And the way we will do this is very intuitive. So what we have done is now, when we evaluate our fitness function, the first thing now we will do is we will measure if the overshoot and steady state error are close. But if these values are not close, then what we did is through simulation, I did find out that certain values of kp and ki will not give you satisfactory results. Your quadcopter will just not be able to reach the steady state, and it will keep on oscillating or even not be at your desired point. So in those cases, what happens is that I've just measured that if the final value of the error is less than 1%, or it's is less than or is more than 1%, then that means that you have not been able to reach a steady state value. And in that case, your fitness value will just be respect what your error is, because that means that at the final value or at the final instances, your controller was not able to achieve steady state, and so it kept on oscillating or it diverted towards that. So what I have done now is I've modified my fitness value. So my fitness value will essentially be all dependent on the steady state error, which is this value. And if it is very high, then essentially it means that it's if the error is high or if the error is low, then whatever that error steady state error is, then that will be basically essentially what your fitness value is. And through my results, I found out that since initially your kp and ki values are not correct, you will have a very low fitness value, which is good actually, because you know that those kp and ki values are not correct. So the way then what you do is you go and you mutate your function. So this mutate function has gone through a lot of iterations. You can see a lot of comments that I've added, and these comments were basically how I went through my observations and what I found out was correct or not. So what I will do right now is I will go through some of the mutation parts. What will happen is, so if you go through your function, which is my code launch, you will see that what we do is we give a value of kp, ki, and sigma ki. We produce a population, and that population then we know the size of that population, and then we give it generation 1, because that's the first generation that we're going to create. We then evaluate our kp and ki values, then simulate the whole system, measure the steady state error and the overshoot, and then we evaluate the fitness values depending upon what we have stated. That if the steady state error is more than 1%, then that means that our system has not been able to reach steady state, and then so all of our fitness values depends on the steady state error, and usually that is very low. And then what happens is that you create a pointer. So now the pointer is essentially saying if we were able to go inside this function or not. And the way I have not the reason why I have not implemented in this particular function is because of some array indexing that might create more issues in the future. So I just wanted to have everything separate. So the pointers are essentially telling you if the function went inside this, or if this if statement was valid or not for each iteration. And the reason why that is essentially if we are going inside this function, then we are not close to our value, or the kp and ki values are not good enough. So at every iteration, if a generation enters this particular if function, you would like to know, you would essentially have an idea of, okay, my function over here or my kp and ki values are not correct. So what you would do then is I created a mutate function which will take that into account. So the pointer underscore will basically tell you if my pointer is 0 or 1. So in cases if it goes inside, it will be 1, and if it is 0, it will not go. So in cases like if the pointer is 1, then you will do something else. You will do a different type of mutation. But if it is 0, then you will do a different type of mutation, which is essentially have you gone inside this function or not. That's what the purpose is. So the mutation function, what it does is like it evaluates the maximum value of a particular generation. So you will give it like the first generation, which consists of a population, and then that population you will evaluate the highest fitness value. You will take that highest fitness value, and depending if the pointer is 0 or 1. So if the pointer is 1, that means that you were not able to get a very good value of your KP or KI, and now you need to change that sigma. So you need to change that sigma. So in that case, what happens is that we create a new mu and we create a new KI value. And those new mu's are randomly generated. So the range maximum value I expect my KP to be, let's say, is 40, and the maximum value I take for my KI is to be 50. So this will create a new mu and it will create a sigma radiation. So for simplicity, we have kept sigma to be between 0 and 1, which makes sense if you have taken any normal distribution statistic classes. Your standard deviation cannot be less than 0, but it can be 1, 2, 3, or more than. So it can be any value greater than 0, but not less than 0. And what happens over here is that we are randomly basically trying to shift this mu over here. We're trying to shift this mu in order to find new values. So then what we do is we generate new mu's, and then we create a new population with respect to that mu, and then we iterate this process. So the purpose of this is that what we want to do is like eventually we will definitely hit a point where our KP value and KI value will be good enough. It will not be perfect, but it will be good enough. And so what happens is that if our KP and KI values are getting better, then we will stop going inside the same function. So our steady state error is now improving. So essentially what I'm trying to do is I'm prioritizing steady state error over overshoot. And then the reason behind that again is that we know from a KP and proportional integral system that we cannot decrease the overshoot error. So the overshoot error will be persistent. So that's why its priority is less. But what I want to do is essentially say that, okay, if my steady state error is now decreasing, then I will evaluate these fitness values and my pointer values will now be 0, which means that I'm not going inside this function anymore. So my steady state error is now improving, which means that essentially I'm now able to achieve my steady state. So I am able to essentially track my system. But now what I want to do is find better values of those KP and KI. So what happens then in the mutate function is that it iterates to these generations, and then when it finds a value of KP and KI that it thinks it's good enough, and the results do tally with that, then that becomes your new mu. So when the pointer value is 0, your mu new is essentially going to be that particular value of your system. So let's say, for example, and I'll go through, I've run this simulation already, and I don't want to run the simulation in this video is because this simulation took a lot of time. So the simulation that I ran consisted of a population of 10 for each generation. So you can see that these are the fitness values for each population. And you can see this over here, the first population, because the KP and KI values were not good enough, that they did not perform well. Then we mutated our KP and KI values. So it did mutation, and you can see that again the fitness value is not good enough. But in the third generation, you can see a rapid improvement. So the KP and KI values are now good enough, and your fitness values are again increasing, which means that now your mu values are better than what they were before. And this should actually show up in your KP and KI values. How are they improving, or how are they improving through the generations? And then you can see that suddenly our KP and KI values are now getting better and better and better. And then at the 1, 2, 3, 4, 5, 6, 7, at the 8th generation, you can see now that our fitness values are very high compared to what we have started with. So this means that this genetic algorithm is now working effectively towards finding a new value of KP and KI, or the new mu, the mean value of KP and KI, and the ranges are now getting better and better. So then you can see that there are cases where our KP and KI values are not good enough. So for example, the first individual in generation number 8 is not good enough. But then in 9, you can see that the results are still improving and they are getting better. Or the individual number 3 in generation number 10 is not good enough. But the results overall are better. You are performing now way better than what your initial guess was. And the reason behind that is your KP and KI values are now much closer to what they were. Of course, if you keep on running this for several generations, let's say you run this for 100 generations, then your fitness values essentially will become better. And this is what I wanted to do actually. I wanted to create a genetic algorithm right now that can improve. So let's do one thing. Let's see if we can just plot our KP values throughout the generation. So one thing that we could see that is, let's say, plot. This might take some time. New pop constant. Can I put this? And so now if you can see over here, this is the way KP values like improved. So you can see that initially in the first generation, so for the first 10 values, KP values are here, then they decreased, then they increased, and then they decreased. And now they have found some stagnation. So you can now intuitively get an idea that your KP values are actually somewhere between 1 to 5 or in this range, but or a bit 12 like that. So these are the growth. And if we run this more higher, we can see that maybe they will settle to a point that which makes much more sense. So of course this depends on the fitness value. We could do similarly for ki and see what happens. Again, you can see that initially your ki values are very large, then they go down, but then they start to average out. They start to get to a value which is closer. Of course, if I run this for much more generations, for much more or a larger population and much more generations, let's say 50 generations, then I do expect my genetic algorithm to come up with a value which is good enough. Of course, then that means that it's not a perfect solution, but we all know that genetic algorithms cannot provide you the best solution. They can provide you the optimal solution, and that's what the whole purpose is. So in my next videos, what I plan to do is I do plan to work more on the fitness function because I still feel like the fitness function is not good enough. But I do now have a very good intuition that my mutation function is at least getting some results, and I might modify the mutation function based on what my understanding of the system is. This, of course, also gets me to the point where this is much more supervised learning than what I would like to do. But the reason behind this is I am trying to push my solution into an area where I think it will work because I have a very good understanding of how proportional integrals and PID controllers work in general. Could this type of fitness function be implemented on another PID controller? I don't know, but I hope so that since the overshoot and steady state are basic things, we could come up with solutions which are much more easier to define too. We could like at the end of this project, implement this genetic algorithm on a different system. This might give us good or bad results. So that is one way of validating if your genetic algorithm is good or not. But intuitively, what I'm trying to do is much more supervised learning than what my system should be able to do. But since this is just a project for a class, we can take this. We can get this acceptable that we are trying to get to a result, and we already know what our results should be. So I know my KP and KI values are somewhere close to 4 and 5, or it could be a better, or it could turn out that there is a ratio system that is working on. So essentially what is happening over here is that the ratio between KP and KI is much better over here or much better over here. So it might be that, or the ratio between KP and KI is not good enough. So we could do this much more in the future and then get better results for that. So my future videos will much more now focus on how to enhance this mutation function or how to get the optimal best values of KP and KI. So in the next, what I do plan to do is that in the coming weeks, I will run this for much more larger generations, and then I will see if these mutations are. So I've not gone through the results of actual systems. So maybe the overshoot is too high over here. I've not seen that, but the fitness value at least shows me that the system is performing well. But again, since I've disabled the simulation, and the reason behind the simulation disable is that I cannot just sit through 100 simulations and see each one of them individual. I can plot the results. I already have the results, but going through them individually is going to be a bit hectic. So I'm going to modify my plot results to see if I can get a better system over here or not, or get a better plot system over here or not. So in the next videos, I'm going to go through those data and I'm going to explain how much of work I've done. But so far, you can see that my fitness values have improved drastically. and they're getting better and better through each generation. So at least at that point, what we can be satisfied with what we have achieved so far. So that's it. I'm gonna stop my video, and I hope you benefited from this. Okay, bye.